the Bohr model. The Bohr model was developed based on that. In a sense, just to make it simple, think of it now as the solar system, but at the microscopic level or the atomic level. So what is it? Is that you have orbits, you have a nucleus, and you have the electrons occupying those specific orbits. Now we're going to move away from the word orbit because, yes, they're interesting, they're helpful to remember. You can still call them between you and yourself, but now the word is going to be an energy level because they are nothing but energy levels. And by the way, also the orbits around the sun are also energy. They're moving, and you can actually measure the energy of the earth moving, etc. So let's actually look at the Bohr model. He developed the model of the atom to explain how the structure of the atom changes when it undergoes energy transitions. He said that the energy of the atom and its amount was related to the electron's position in the atom. Okay. So if you look here, and I'm going to make this slightly bigger. This one is going to be, okay, here it is. So if you look here, here's the nucleus. And those orbits are what we call energy levels. Okay, why is this not moving free? Okay, so this is an energy level. So you see it, see that one right there, the first one, that's called the ground state. Or you can think of it as the first energy level. And then you have the second, the third, the fourth, the fifth. So what he said is that they occupy specific energy levels, and it was related to the electron position of the atom. Well, the first one here has the least amount of energy, and electrons love to occupy those. Why do you think? Because they're closest to the nucleus. Oppositely charged, so they want to be as close as possible in a very, very simple, explaining it to the very, very simple language. Second energy level has more energy, but it's the second one preferred, and then the third, and then the fourth, and then the fifth. As you move out, you notice that you have now more space, and you will see that more electrons are going to occupy these. Very well. So this explains to us when atoms or molecules absorb energy, the energy is often released as light energy. So fireworks, neon lights, all of those actually occupy this or are explained by this. Think about it. So imagine you heat an atom, and when you put in an energy, let's say we want to look at red right here. So what happens is, let's say the electron was here first. And then I put in heat. You know, heat related to kinetic energy, it's going to move the electron to the third energy level. Now, this electron is not happy. So when the heat is absorbed here, the electron now wants to jump back. We say it wants to relax. Really, that's the word for it, relax. So it's going to go from the third energy level to the second, go back. And when it goes back, it has to give up that exact same amount of energy. It has to give up that exact same amount of energy. And then when it does that, it's going to release it in as light. This is light, but it's going to be at 657 nanometers, and that corresponds to red. Well, what if you have an electron now in the second energy level? You put in heat, and it was promoted to the fourth energy level. Well, after a while, the electron wants to now go back. Well, if it has to give up exactly the exact same amount of energy, and when it does that, releases it as light, but this light is at 486 nanometers, which corresponds to blue-green. And violet is again from 5 to 2, and it's 434 nanometers. And you can see that this is the most energetic. Now, you should understand why this is the most energetic now. Look at this. This is a bigger leap. Call that a quantum leap. So this is a bigger leap. This is from the fifth energy level to the second. From the fifth to the second. So violet is from 5 to N2. And in this case, energy is released the opposite energy is absorbed. So make sure you understand this. Be able to, if I give you the transitions, you should be able to say that yes, if it's from a lower to a higher, it means you have to put in energy to move it. And if it's from the higher to the lower, it has to actually give up energy to move it. Same thing here with red. If you look at red, it was from N2 to N3. So this is energy absorbed. And then from N3 to N2, energy is released, and it's released as red. So this is how fireworks work. You have a different metals in there. They display what we call an emission spectrum. They have different absorption, and they give you different colors when they're heated. I mean, that's the process, right? Is that they explode in the sky because, again, they reach a certain temperature, and then electrons absorb the energy. They move to let's say the third energy level, then relaxes. It gives out that energy as the color red, violet, blue, green, whatever it is. So actually, what's interesting is color is really in your eyes only. If you think about it, there's outside of your eyes, there's merely just wavelengths of energy, of light. So 657 nanometers is just that wavelength right here. Like right here. Or maybe this is a better picture here. Looks right, it's colored red in this diagram, but it's not. It's just a wavelength of energy. And the same thing with the green and the bluish one, or the violet. So you have, outside of your eyes, those are just, again, waves with various wavelengths, and they have again, those specific wavelengths can be interpreted by the eyes. And your eyes, they have rods and cones. And if you remember that process from anatomy, physiology, and you have something called the rhodopsin cycle, they actually create an interpretation in your brain, in your mind, and that appears as the color red. And for example, your eyes are much better than, let's say, a cow. A cow can only see, from what we know, from the scientific consensus, can only see shades of gray. They can see black and white and shades of gray, but they can't see red, blue, etc., because their eyes are not as advanced as our eyes, their eyes, and they can't see those specific colors very well. Each possible electron orbit is characterized by a quantum number. And again, there you can see how close they can be. The farther away from the nucleus, you can see that they get bigger. This brings us to an important topic here, and what I would like you to know with this is really understand these three series, right? So anything, pretty much anything from a larger energy level to the lowest energy level, N1, that's called the Lyman series, and that can only give you violet, ultraviolet, UV. The Balmer series is the most important one because this one is anything from above 2 down to 2. So if you see, we just talked about red, it's from 3 to 2. Green can be from 4 to 2. Violet and blue, so on and so forth. And then you have the Passion series, and that gives you the infrared. And you can see that infrared is from down from, let's say, 4 to 3, 5 to 3, and then 6 to 3. And notice one thing. Notice how the bigger the leap, the more energy it is. Ultraviolet is much more energetic than infrared because look how big that leap is versus that.